Recording. So it is November 28th, and we're just talking about review for the test. So what types of questions do you guys have?
Could you clarify the difference between capital omega and lowercase omega in the equations you have up there?
Sure. So in these equations, like for the first one, if we have a sum of moments about 0.0, then in general, these are going to be the same. So pretty much if we're doing a fixed axis rotation, we're going to choose this to be whatever that 1 omega is. So choose this to just be the same, right? So it's basically just going to be this omega. Okay, so that's for a fixed axis type of problem. So that's going to be something. Let me just check my things here. So that would be something like, you know, let's say we're looking at a problem like this one. So which of those two types of equations do you think would be best to choose? So sum of moments about O like a fixed axis, or sum of moments about some point P, which could be A, it could be 0.0, or it could be even the overall G of the system. So which one of these two equations do you think would be easiest to use to solve this problem?
I'd probably pick the first one.
Yeah, and that's what I would as well, right? So that's really the times when we've used it. Otherwise, you know, if you didn't pick that one, you're going to have to figure out where the overall CG of this structure is, right? And that's going to be a little bit of a pain. So you'd have to kind of go through and figure out, you know, where's my overall X bar by doing a sum of MI xi over the sum of the masses, right? And then you'd have to do the same thing for y bar and as well as z bar. And then you're going to have to move everything to that, which, you know, is going to be, you know, I don't know, somewhere like in here. And it's just going to be a big pain to try to get something so that you can use, you know, this guy here to figure out what the overall CG is. So really probably the easiest one to use is going to be that first one, right? So we'd end up doing it with this. So if we're doing this one, then really the only omega that we have is in what direction?
Yeah, it's the omega z.
Yeah, so that's going to go to 0, that's going to go to 0, and then we're really going to use in this the omega. So basically it's going to be an omega z that I'm going to put in right there, which is essentially this omega right there, right? And in this case, it actually acts in the minus z direction, right? That's going to be 0, that's going to be 0. Okay, so omega now, if I say it's increasing, what does that mean? Where would that go into the overall problem?
So your HO dot wouldn't be 0.
Correct. So now I'm going to have the same I, right? So basically I'd put this same I in there. And remember, this I is going to be about 0.0, if that's where I've chosen, right? So this is the I, this whole vector here is for this axis system. So this is the I for the XYZ system centered at O, right? So this is going to be centered at O, right? And that's when we went through and we said, okay, well, I can figure out what that mass moment of inertia tensor is. Remember, we kind of went through and we said, okay, you know, we figured out what my coordinates are, the XYZ coordinates for this thing. So then this term down here is just going to be 0, 0, and then whatever omega dot z is, right? And so that omega dot z is basically, that's going to correspond to whatever that omega is increasing with. Okay, so maybe that's a minus 2 radians per second squared. Okay. Does that make all right sense to you?
Yeah, and so to clarify a little bit, for that HO dot, where you kind of drew the arrow down to the I inertial tensor, that's multiplied by omega z dot, right? That's what that is.
Correct. Yep,
Okay.
that's right here. That's the omega z dot. And of course, this I is the same I as this I.
Right.
Right? Those two are the same.
and you wouldn't have to cross that with like a capital omega dot like you are with the other one, would you?
Nope, because this is talking about how that that angular momentum vector is changing with respect to whatever my rotating system is. So if I'm attached to this kind of this X, Y, Z, and it's rotating around with the shaft, then the only change in that angular momentum vector is going to be if the omega is increasing or decreasing.
Okay, gotcha. Perfect, thanks.
Okay, so are there any kind of questions? Oh, and Clovis was just asking what I said, right? Are those two I matrices? Yeah, they are identical, and they will all, pretty much always end up being identical. Okay. So then, let's say what happens if I go then to a problem like this? Okay, and this was some of the confusion in class and some of the confusion in the office hour. So we talked about this some before the break, and we solved a couple, and I've posted a few that are similar, and some of the example problems that I have were posted from a few years back when we were teaching it a little bit differently. So there's still the same basic things in there, but sometimes we took some shortcuts that might have confused you a little bit. So let's say we have a problem like this, right? So how many rotations do I have to this thing? Right, how many omegas are involved? Yeah, so we have two, and they're kind of, daisy chained, or you really have, one thing to look at is, does omega 1 change its direction due to omega 2? Right, so is that the case? Yeah, okay, so basically when I do these, which one of these two primary expressions for some moments do you think I should end up using? What's the best one to choose? First one or the top one or the bottom one? Okay, so so we got some disparity there. So Ethan's thinking the first, and Clovis is thinking the top, right? So in general, when I do that sum of moments one, remember like we talked about in class and the others, I really only use those for a single axis rotation when we're talking about something, sorry, I'm going up and down, something like this. Okay, so that's the only time that I use this top one. Okay, when it's a single axis rotation, like here, that's an asymmetric one. Okay. There are some other cases where you can still use it, but in general, if I've got a setup like this, I pretty much always recommend you using this one. Okay, so to use the one where we have it about an arbitrary point, and since I'm asking to find the dynamic loads at point C, we can do that fairly straightforward, where that's going to be C, right? And now this is going to be, from C to G. That's going to be the R vector. Okay, it's just always really easier to go about doing things about this centroidal axis. Okay, when we solve them, that's pretty much, this is really how we've solved these types of problems all the time, right? And the reason again is because I have these two different omegas. I have an omega 1 and I have an omega 2. Okay. Do you see the difference there? The first is where I have these two bearings, right? But like at D and like at E, but I don't have another rotation going around like this, right? So for all those problems where we have just a single bearing, a single shaft, and I've got the bearings on either ends, and then I just have it going, only one omega, and then maybe I've got, some different things that are going off of it like there. I've got cams, I've got whatever, but the difference is it's not going around, right? It's not going around like this. Okay. Okay, so Taylor's asking, what would I end up doing for this, right? So in that case, then I'm looking for well, first of all, where is G? So if I'm just talking about the disk and I'm not giving you a mass or anything for the two arms, right, then I'm worried about the acceleration of the center mass of the disk. Okay, so I could then write that out. Well, acceleration of G, right, is really equal to acceleration of C, which is this point down here, plus omega cross R, all right, plus I've got potentially an alpha cross R. Okay, that's just our relative velocity equation. Now, what omega is making A, so the question again is what omega is making point A linearly accelerated? Yeah, so it's just going to be omega 2. Does that make okay sense to everybody? Okay, and then we see that acceleration of point C is just going to be 0. Okay, and then what alpha is going to make point G, which is the same as point A in this case, right? Because we're looking up here, so that's really our point G. What is going to make point G linearly accelerate? What alpha would make, so A2, but, right, so Clovis is saying, well, if it's not constant, so in this case, my alpha here, that's going to be 0 because these are constant, right? And more specifically, omega 2 is constant. Okay, so then how do I figure out, what's my R? Can I figure out what my R from C to G is, right? What is that going to end up being? Yeah, so I got to use a little trig, but remember, it's just a vector, so it's not too bad, right? It's just a -9, and that's in the k-hat direction, right? And then plus, I've got another 9 in the j-hat direction. Okay, and then that's going to be crossed into whatever I get for my AG term up here. Okay, is that part okay so far? Okay, so then, right, I've got my XYZ, so now I can look at these terms. So what should I do next? What do I have to decide about next? I mean, I could, and I'm actually kind of skipping out doing the FBD and the KD. Yeah, so Val's kind of on the same line of thinking that I am, is we have to decide what's my omega that I'm going to use. Okay, so the question is, what's my capital omega? And remember, I have to choose one so that my inertial matrix doesn't change. Right, so could I choose my capital omega to just be omega 1? No, because that's farther out, right? I can't just rotate with omega 1. I'd have to have both omega 1 and omega 2. Could I just choose omega 2? Yeah, so I could do that. So if I chose just omega 2, okay, so then capital omega is just going to equal omega 2, right? So if we do that, then I would look and say, okay, well, that means omega 2 is in which direction? Right, it's in the X, so that's what this is going to be. And then what would I put in for capital omega Y and capital omega Z? Yep, so that's going to be 0, and that's going to be 0. Okay, and then what do I put in over here? What do I put in for my little omega vector here? Yep, so this is now going to be, let me see, I don't think the z is the omega 1. Which direction is that in? Yeah, I agree with you there, right? So this is going to be now omega 1. Do I have any omega about the z direction? Nope, so that's going to be a 0, and then the omega x is going to be omega 2. Is that all right so far? Okay. And then let's look at my inertial terms, right? So that's about the g. Remember, that's what the bar means. So Ixx, Ixy, Ixz, all those. Do any of those terms go to 0? So if I'm going about g for that disk, right, then remember, it's kind of like I've basically moved these, and I could put, like, if I want, like a little prime on there, if that helps differentiate. Right, so basically, if I look there, then the x prime, y prime is a plane of symmetry. The y prime, z prime is a plane of symmetry. And really, even the x prime, z prime is a plane of symmetry. Does that make sense, everybody? So that means I have what type of axes? Starts with a P. Yeah, so those are going to be principal axes, right? So all of these terms are going to 0. Do you guys understand that? Okay, so I'm going up to point G, right? And I still have my same directions for the X, Y, Z. Yeah, so remember, when we use this equation here, right, I don't use a parallel axis because this is really taking care of it. Right, the R cross MA takes care of that. So I don't need to use a parallel axis theorem. And in fact, it would be wrong to use a parallel axis theorem. Okay, so now the final thing I have to think about is this term right here. Okay, so the question is, if I'm just going around, and remember what we did is we're saying, you know, I'm only rotating with the omega 2. So I'm only, you know, so maybe I'm just standing here on this bar right there, right? And I'm trying to figure out what's going on with respect to me, right? So I'm not rotating with the disk. I'm only rotating around with this omega 2. So the angular momentum, right, I want to look at it with respect to me sitting there. So one angular momentum part is going here, right? So remember, this is really my angular momentum vector HG. So when I do that out, I'm going to end up with one of them that's going to be about the x-axis, kind of pointing that way. So as I rotate around with this guy here, this vector is always going to be like to my right. Do you understand what I'm saying? So if I'm rotating, you know, I'm rotating around like this HG is always going to be to my right. Does that make okay sense to you? And Val, Ethan, Taylor, you guys on board? Alex? Okay, good. So then the other question is, like, it's not changing direction, but does it change magnitude any? Is that thing getting bigger or smaller? No, because omega 1 and omega 2 are constant. Okay, Then, as I'm looking here as well, right, the other h vector is pointing straight up. Does that make sense to you? Because this is rotating around, it's got an I. So the other part of my hg vector right here is going to be pointing straight up. Okay, so does that change as I rotate around like this? Does that change with respect to me? Is that still just pointing basically straight up? Or is that changing direction at all? Yeah, so it's not changing any. Is it changing in magnitude? No, because omega 1 is constant. Okay. So for this problem, that guy goes to 0. Okay. Was there a question there? Okay. So do you guys feel like you could work out the math on this? Okay, so now let's look at it. What happens? Shoot, I should have made another one. Yeah, so there's two cases where that could happen, Val, where the hg dot would not go to 0. So let's say we're looking at, oh, maybe I did do 2 of them. Let's look at this problem again, but in this case, instead of setting omega equal to only omega 2, we're going to set it equal to omega 1 plus omega 2. Okay, so now it's going to be equal to both of those. Okay, so this term here is still the exact same as what we did on the other page. Exact same thing, right? Doesn't change at all. My inertial tensor is still, fortunately, the same, right? Because once I put this guy up like a, y prime and a z prime and an x prime, right, then even now that I'm rotating around with the omega 1 as well, I still have the same inertial tensor. Okay, so finally, what I've got to do is say, well, now I'm kind of riding on this guy right here, right? But now I'm spinning around as well. Okay, so if I'm setting it to omega 1 and omega 2, then do I have any omega in the x direction? Do I have any capital omega in the x direction? Yep, so that's going to be omega 2. How about in the y direction? Yep, that's going to be now omega 1, and then this is the z is still 0. Okay, and then I have the same thing over here. This is going to be the same as it was last time. So it's going to be omega 2, it's going to be omega 1, and that's going to be 0. Right, so it's the same thing as we had here. Right, so the omega 1 there, but the difference is now, first of all, in this column. Okay, so this is when we set it equal to both of them. Is that part okay so far? Okay, so now where the difference comes in is if I'm sitting there looking here, then, and I'm rotating around with it, right? I've got one HG part that's still pointing straight up in that Y, right? So I got an HGY, and as I rotate around, even if I'm spinning around like this, right, that part of it's still kind of pointing straight up, right? So I do have an HG. That's not changing anything, right? It would change, again, like I was saying before, it would change if omega 1 or omega 2 is going to 0. Okay? So what I'm going to do with this guy here is I'm going to have my same inertial tensor, right? So this is still the the I bar. So it's going to be the same inertial tensor as here. Okay? But then for my omega, here's what I'm going to end up having to do. Because remember we talked about this part of like this is my HGX, that's my angular momentum vector. Well, if I'm up here and I'm rotating around like this, then this vector is not always pointing to my right anymore. Right, so I'm going to go down, I'm going to look at the old case, right? So in this case, remember, I was just writing here, and that vector was always off to my right, okay? But if I am now attaching my axes to rotate with both of these things, then as I go around here, this part of my H term is no longer pointing to my right, so once I get, if I rotate around, at first it's to my right, but then it might be to my back, and then it's to my left, and then I'm over here, and that's to my back. So, everything can change around with there, and how we end up handling that mathematically is just by doing what we had done before, where we said, well, I've got omega 2 is making, and that's, remember, in the I hat, that's making omega 1 change direction. That was in my J hat. Okay, so then I get out of that omega 1, omega 2, K hat. Okay. Do you remember doing that back when we were doing angular accelerations? So then here, that's what goes into this term right here, omega 1, omega 2. Okay, so in this case, my H dot G is not 0. Okay, and that's just because of how we ended up choosing our capital omega. Okay, and then the other way that could change is if omega 1, right, so if omega 1 had some sort of change, right, some sort of angular acceleration, then that term could go in there, right? So if omega 1 was increasing or decreasing, right, that term would go in there. That term wouldn't be 0. The same type of thing for omega 2, right? So I could put something in right here that would be there if omega 2 changes, okay, is not constant. Okay, so does that answer your question, Val?
Yeah, it does. And just one more thing. So if we had chosen our capital omega previously to be just like omega 2,
yeah,
we wouldn't need that omega 1 times omega 2 in there.
Correct. In fact, it would be wrong to put that, right? And so this is where we just chose it, right? This
right.
was when we chose just omega 2.
Mm-hmm. Yep. But like, say if there was, say, like an acceleration in omega 2, so we'd kind of still be using that method, but that part would just be blank, right?
No, if you do have a change in omega 2, then this vector is getting bigger, right? So even if I'm sitting right here, I see that vector getting bigger and bigger and bigger, right? So this could end up being, the same I here, right? So that's going to be my same I bar times it would have an omega, the X was omega 2, right, dot. So that would be here, and then this would be omega 1. Oh, yeah, omega 1 dot, and then this would be 0. So this would be if omega 1 and omega 2 are not constant.
Okay, gotcha. Yeah, that's what I tried to say. I said it wrong. Sorry.
Okay, no worries. Yeah, so there, those would be the same in both of these cases. So if my magnitude of my omegas is changing, then that part would be the same, right? So this would be the same as this one, right? So those two would be the same, no matter which one, what omega I choose. Where the issue comes in oops, sorry, is right here. Right, and that should make some okay sense because I have to get the same answer no matter which way I solve it, right? So now the difference ends up kind of coming in here because remember in this case I had omega 2 and omega 1, right, when I did it, whereas in this case I only had omega 2. So this whole second term here is going to be different. You know what I mean? So it's going to right, when I look at this term, right, that whole term is going to be different because this omega 2 is here, whereas in this one I have omega 2 and omega 1. So when I do this whole term, it's going to be different. This term is the same, right? This term is different, so that means this term is going to have to be different as well. And where that comes in is because in this local frame, when I'm writing up on the top, that H is changing. Okay, so hopefully that helps clear up a little bit of, when I use this one, which again is really only in the single axis rotation. I don't have both an omega 1 and omega 2. I don't have both, some sort of planetary and a spin axis, right? Where this one is when I have two different axes of rotation going around, right, that are kind of combined, right? So we've done a decent number of both of these types of problems. Okay, more questions. About 5-ish more minutes or so. Okay, anybody else? Do you mean just the overall time derivative of a vector? Is that what you're talking about, Ethan? Back to the Q. Oh, gotcha. Back to the question. Sorry. Let me see here. Are you talking about this one here? Sorry, when you said Q, I was thinking of that whole time derivative of a vector deal, right? How we derived it before. No, so in this case, because I ask about it at C, right, then at point C, because you've got a lot of stuff that can go on there, then what you would do is, hold on for a second, is you would end up putting in, if I did out my free body diagrams for here. So here I was just asking the dynamic loads at point C. So you could end up doing, basically like some sort of a moment in the Y here that could end up being some sort of torque. And then you can do like a CY there. And then you could do the same thing in the X and the Z. Okay, and I think I actually solved this whole one out for you back in like lesson 22 or 23, and so that's posted. Well, the one thing you might end up having is some forces due to the acceleration of the center mass at A. You know what I mean? So like I've got, since I have I do have an acceleration of this, which is going to essentially be a normal acceleration, right? So I'm going to have some sort of an acceleration of G going in that way. So that's going to mean there's going to have to be some sort of overall force acting down this way to accelerate that towards the center. Okay, so why don't you guys study a bit more, go over some other problems and see if you have more questions for tomorrow. We'll do the same time, same channel. Okay, so I will also post this recording as soon as it goes through all its different translation type of stuff, and I have to load it up to YouTube, and then I'll give you the link. Okay, yeah, you're welcome. I'll talk to you guys tomorrow. All right, have a good night.